Topic for today is unlock the value of polymer 3D printing. So in this session, what we will be doing, we'll take a quick look at the different 3D printing technologies and take a deep dive into the FDM or FFF technologies, how it has gone beyond the actual simple prototyping and to making the production part, and how professionals are really using the FFF technology in making the functional parts, and that actually even like have the support the sustainable manufacturing and bring new ideas to life very fast in a more fast paced manner. We would like to this would be a very involved session. We want you to be very involved in this. We will have a dedicated Q&A session at the end, but no, feel free to drop your questions anytime in the chat box, and we'll try to group them at the end of it and try to answer as much as possible. And we'll have to make sure that this interaction is much more meaningful. That's the whole agenda of the day. The quick note, today's webinar has been recorded, and by participating in this webinar, we accept for distribution of this in the learning community. So having said that, with that introduction, I would like to introduce the speaker of today, Mr. Manish, who is heading as a senior product engineer in Wipro 3D in the product development department. Manish comes with 10 years of experience in polymer additive manufacturing and the deep expertise in most of the additive manufacturing technology on the polymer side. Know in and out about the the machine development and the material usage in that. And for past 5 years, he's deeply involved in R&D of the product and innovation, and delivered very high impactful solution to the industry, solving some of the complex solution, providing some solution to the complex problems what he has come across this years. So here he'll be focusing on the material, the processes, how he's going to optimize the product. It will be excellent. I think he's a very excellent guide for today's topic. I'm sure that the knowledge what he's going to share is going to be of much use to all of us. So with that, I require please ask Manish to join and take forward and enrich us with his experience. Over to you, Manish.
Thank you, sir. Thank you for your warm welcome, and thank you for the introduction and the warm welcome. So good afternoon, everyone, and thank you for joining today. Today, we have an exciting session focused on polymer 3D printing, a technology that has been transforming industries worldwide. So we would be covering by starting with some introduction on 3D printing technologies. We'll cover various 3D printing technologies on how they function, and we'll focus a little bit on polymer 3D printing specific to material extrusion that is considered a revolutionary technology across various industries. Next, we'll explore how this technology actually drives innovation, cost, enables complex designs that were previously impossible with traditional methods. Then we'll also dive into some of the real world applications, the challenges, the solutions, the value that it brings across industrial manufacturing, healthcare, defense, and various other sectors. And finally, we'll also look into some of the innovation enablers, specifically focusing on material extrusion technology and the factors that is fueling the growth from advanced polymer materials and improved printing technologies, and also the integration with digital manufacturing ecosystem. So let's dive in. So to begin with, I just want you to brief a little bit on 3D printing altogether. So we all know additive manufacturing, or the AM, is changing the way we think about how we make things. So for people who are very new to AM, I would like to take a little bit basic, in which I would like to take across all the different categories of AM as classified by ASTM. It is basically categorized into 7 major categories, and each one works differently. Today, I'll walk you through all the 7 and how they work, where they are used, and why actually they matter. And I will specifically focus a little on the polymer technology, more on the material extrusion, and then I'll take you through all the various case studies and some of the industrial challenges, solutions, and the value that has been brought into this. So let's start with vat polymerization. If you want to understand vat polymerization, you should basically picture a tank which is filled with liquid polymers. You basically have a laser or a projector that shines light in a specific pattern in a specific area, which cures the resins layer by layer. Basically, the resin will be in liquid form, and once it's exposed to this specific laser or the UV rays, it converts or solidifies from liquid to solid. So it's like drawing light inside a pool of liquid. So technology like SLA, DLP, or SLA, nothing but stereolithography, and DLP is also called as digital light processing, use this method. And the result is the parts come with incredible detail and smooth surfaces, and it's perfect for like jewelries, prototypings, dental models, some of the end use application in automotive. In fact, there are various materials that have come in the polymer space that they are actually being used in the functional end use case. And then we have another technology that is being called as material jetting. So material jetting, you can imagine a regular 3D or a 2D printer, inkjet printer, but instead of ink, you have something in terms of polymers that is being droplets of polymers that is being spread onto a platform. Then once the polymers are spread into a platform, and then the UV light cures these droplets. So what's amazing here is actually the multi-material capability. You can actually print rigid, flexible materials together. Even you can print multi-color capable parts as well. For example, multi-jet fusion, which is called as MJF, where you can have parts which with multicolors, and you can actually think of some realistic prototypes and for consumer products, for medical models. So this is one technology that you would go to if you need high detailed and end use application parts. However, there are some downsides, the main thing being, it's a little expensive, and in certain, it is limited to a certain materials. There are no wide varieties of materials in material jetting, but uh, materials like nylon and compositions of nylons are available, and thermoplastic polyurethanes are available, where the prototype itself makes it look and feel like the final product. So that is something that is unbeatable in material jetting. Then next, coming to binder jetting. So here, basically, we start with a bed of powder. It could be metal, it could be sand, it could be ceramic, it could be polymer. A liquid binder is actually sprayed and glued together so that these powder particles bind together and in the specific layer, and this repeats layer over layer. So after printing, the part is mostly little fragile. So there is a process, post-processing technique, where you called debinding and sintering, which makes the part more rigid and usable for end use application. In fact, I have also seen materials like sand molds being made, and also some metal parts are possible using binder jetting. In fact, it is fast, it's cost effective compared to the other metal printing technology. This is a little bit comparatively cheaper and easy to handle. Of course, handling powder is still a little challenge in these technologies. And yes, of course, with all these extra steps of post processing, the strength comes with it. Then you have something called as powder bed fusion. This is where is your SLS or SLM or EBM, all these process come into picture. So in this process, basically a laser or an electron beam fuses powder particles together on a powder platform. So this is actually a workhorse for metal and polymer parts both. You get actually strong functional parts and precise, and you can also make aerospace grade parts, materials, and medical implant grades like titaniums, and high performance automotive parts often come from these processes. And powdered bread has a little bit of challenge where it's a little expensive. It needs a controlled environment, and also handling powder safely is a little bit critical. So this is where powder bed fusion comes. And the next is the sheet lamination. So in sheet lamination, you basically have sheets of material. It could be paper, it could be composites, it could be polymer, sometimes even it could be metal, which are stacked and bonded together using adhesives or through welding or through laser. It's being cut, and then there's some adhesive that joins them together. So whatever is the excess material is cut away to form the shape that is required, layer over layer, to get the part out. And this is specifically very good for making large parts quickly at a very low cost. So laminating, basically it's like laminating sheets of metal or polymer together. Of course, there is a trade-off in this technology where the mechanical properties are not that strong, and when compared to the other methods, and complex designs are still a little bit of challenge. It's not possible in this technique. And the other is the direct energy deposition, so, or DAD. This basically mainly focuses on metal powders. It's basically a laser or an electron beam melts the materials as it's being deposited simultaneously, or it could be a metal wire which is fed through the melt pool. And DED is actually being very fantastic in repairing of parts and adding of features, even for large scale parts, large scale, say aerospace parts. This technology is the go-to, even for repair of certain components, aerospace components, is possible using DEDs. I have seen repairs of turbine blades instead of completely replacing them as well. But of course, there's downside where there's complexities involved, or where precision is needed, or even when there is say a good surface finish is required, then this technique mostly requires a post processing beyond the deposition. And last but not the least, the material extrusion, which is the most widely adopted and widely known technology. It's either called as FDM or FFF, fused deposition modeling, or fused filament fabrication. So this technique basically pushes thermoplastic filaments through heated nozzles. It builds parts layer by layer, line by line, layer by layer. In fact, this is the most accessible and affordable AM process. It's extremely great for prototyping, and even the advancement in this technology has come so far that it's being used in custom jigs, fixtures, low volume productions, end use applications. Of course, there is a little bit of limitations where the accuracy and surface finish are not that great when compared to other technologies. But for quick and cost effective solution, it's hard to beat. This is the technique that you need to go. So in today's sessions, I'll focus mainly on the polymers and the uh, value that polymer printing brings to industries, specifically the material extrusion technology. In fact, polymer 3D printing has evolved from like prototyping stage to mainstream manufacturing solutions, because the global additive manufacturing market is actually projected to reach billions in the next few years. And with polymers leading the charge due to their versatility and cost effectiveness, it drives demand for customization and lightweighting components, sustainability, because in certain thermoplastics you can recycle them, and industries like automotive, aerospace, healthcare are rapidly adopting this technology at scale. So that's something that we are going to discuss today. So if you look at the values, you can summarize. I mean, I would focus mainly on this eight key values. So because polymer 3D printing is not just about making parts. It's transforming how industrial design can be taken up to end use application. And today, these eight key values: the design flexibility, the ability to rapidly prototype, availability of rapid or diverse polymer materials, and some of the innovation that has come through these materials, and where it is being used in the functional application, and majorly because of cost effectiveness and the reduction in wastage, and in fact the lead time is also reduced. So all this key eight critical points is what I'm going to talk about, and how the value it is driven in different industries. And if you look at the first, design flexibility, so traditionally, like manufacturing, it often limits to uh, the the limitation of the creativity is limited, like because of tooling, because of the machining constraints, and these barriers are actually removed by the polymer 3D printing. So imagine creating a part, say with internal cooling challenge, or you want to have lattice structures. So things would be extremely impossible or very costly when we go with conventional methods. For example, in automotive, engineers print complex air ducts that improve airflow without adding any weights. So in those cases, definitely 3D printing comes into picture. And in if you look at in medical sector, patient specific surgical guides are printed to actually fit the anatomy of the patient, and that flexibility is what it delivers in your design. And in this way you can focus more on the performance and innovation and not just be limited by the manufacturing limitations. And second is the rapid prototyping, and this is widely adopted across industries. The very critical in product development. In fact, we use day in and day out for rapid tooling and prototyping, and it allows to go from concept stage to physical parts in hours instead of weeks, literally in hours. And think about consumer electronic companies and certain uh, say uh, say end use application where you want to test and feel the parts. For example, we have worked with certain companies. We are building pods that help realize their designs quite quickly. So instead of waiting for molds or tooling, printing these parts overnight and testing them the very next day or iterating very quickly, the speed of development is extremely high, and even the cost is extremely low, and it really actually accelerates the time to market. And that is why industries like the aerospace, the automotive extremely rely heavily on this polymer 3D printing during design validation. And also if you look at the availability of materials, so there are diverse polymer materials available. So we're not just limited to basic plastics anymore, because when polymers were printing was started, it was very much limited to PLA and ABS kind of materials. But today polymer 3D printing offers materials that are heat resistant, that are chemically stable, that are flexible in nature, that are even biocompatible in nature. In fact, in healthcare, biocompatible polymers are used in implants and even in the prosthetics. So it needs to be screen friendly and implant friendly. And high performance polymers like PE, Galtem, which can actually withstand high temperatures and very harsh environments. So all that is possible mainly because of the availability of material. So there is wide adoption in this polymer space. And then we also have some of the innovation enabling materials that are present. In fact, we have worked with one of the largest pump manufacturing companies to be able to uh, uh, print along with conductive polymers. So if you look at this image, it kind of gives you a picture. Basically, it's a non-conductive polymer along with conductive polymer being printed together. So here, if you see, it opens doors to a wide range of applications, from smart devices to smart sensors. Being able to innovate using conductive polymers, gives you a very good uh, upper hand in your product development. And of course there are more innovations happening in this sector. And then we also have functional end use parts where the 3D printing has, like I told you, has gone beyond prototyping. Today industries actually produce end use applications. There are companies which are using custom made brackets for the bikes and certain parts, plastic parts, which were conventionally made now, which are rapidly iterated using 3D printing. And also, since the technology itself is so affordable and available, that the amount of waste that is being produced is quite less. And in fact, if you look at, if when you compare with conventional manufacturing, its tooling expenses is significantly high, and the amount of material wastage is quite enormous. So that is where printing has come into picture, and the need for uh, you know quick iteration, quick prototyping without losing or wasting material, and quickly you can recycle material. In fact, there are certain techniques, thermoplastics available which can be quickly recycled also. So that is where it's a win-win situation. It gives you a uh, edge over sustainability as well, right? So the other thing is also the overall lead time. Like if you look at uh, how industries work was, there is always a bottleneck uh, because of the timeline it takes to produce parts. Now, introducing 3D printing into their industry has actually eliminated that bottleneck, and now parts are required in need and on demand. Also, there are no more inventories kept. Like when there is a requirement, people can print and produce and send as and when required. And even for scalability level, if you look at it, uh, from small batches to significantly high volumes, you can definitely go with 3D printing, and which can also be beneficial in terms of cost. And it's okay to run small batches because not every sector actually needs large volumes. They also work in short batches, specifically in medical industry, where you see it's tailored to a specific patient, right? Individual patients, or even the consumer product where you want to personalize things. So companies can produce exactly what is needed when it is needed without overstocking or even wasting any resources. So these key 8 key elements or values are the why polymer 3D printing is actually transforming industries. And it's not just about making parts, it's about rethinking manufacturing for the future. That is where the industry is going towards. And now, uh, now that we have explored these values that it brings in, and let's see how the industries have actually taken up 3D printing and leveraged the polymer 3D printing and come out with success stories. So I'll give you some real world success stories and examples and how polymer 3D printing has transformed the industry's grounds up. So let me take you through one by one. So here, if you look at this, this is a real world example that shows how polymer 3D printing actually solves critical manufacturing challenges. So here the problem actually starts with frequent breakdowns. This is actually a roll mill component. If you see on the left, it's a roll mill where there is a small component uh, which is a braking component, which has a frequent breakdown. And and why exactly is this braking system is failing is because during assembly there is no way to actually assess the design under actual functional conditions. So in other words, if the team weren't able to actually simulate how the braking system would behave in real world, so before putting into real service, right? So this led to actually repeated failures, costly downtimes, and it literally brought frustration in the shop floor. So every breakdown meant production delays and increased in maintenance cost. So here's where polymer 3D printing came into picture. Instead of waiting for expensive metal prototypes or relying on some theoretical calculations, and the team quickly decided to rapidly prototype the braking system component using polymer 3D printing, ran multiple design of experiments actually to test different geometries, tolerances, the assembly configurations, because polymer 3D printing is very fast. It's cost effective. So you can put the part for print today and you can get the part tomorrow, and they could print, test, tweak, reprint again in just matter of hours. Before it used to take weeks and months. Now with just a few hours you're able to iterate. So this iterative approach allowed them to simulate the actual function of the assembly stage, and something that was not possible before happened. And the overall impact is where a highly efficient braking system that actually reduced the breakdowns. It ran the production line very smoothly. Even the maintenance cost dropped drastically, And also the team gained some confidence in their design process. And beyond fixing the immediate problem, the approach has actually changed the way companies think about design validation. So instead of waiting for failures, now they use polymer 3D printing to predict and prevent those issues before they can happen. So this is very interesting. And then next, we also have a story or a case study where actually a hydraulic manifold. So it's a very another interesting story. It shows the power of polymer 3D printing, where it has solved actually a complex engineering challenge. So the challenge here was integrating and validating a new manifold design. So the with if you see the manifold, it's a cut section of the manifold which has intricate channels that can be extremely complex when you want to validate in conventional methods. So validating such designs becomes extremely tough because you need expensive tools, and machining is not just possible. Like you need to break it into multiple parts, join them together later. And if the design doesn't work, then again you have to start over again, and the cost and time and money wasted is tremendous. So in this case, the team actually needed a way to evaluate multiple design options quickly without committing to any full scale production. So here's where the printing came into picture. Instead of waiting for weeks and months together for prototypes and printing these parts, the manifold geometries were evaluated quickly, and internal channels, the layout, even multiple material options were evaluated, because nowadays materials with different configurations are available, like different strength requirements are available. All of this was possible within the same machine in the shortest time frame, because uh, that is the you could say the availability of this technology right now. And if you see the final result, they came up with the best performing design in just 3 weeks, a process that would have actually taken months together if they had gone with the conventional technique. So that there has been a major impact in the lead time. If you look at the concept stage to production stage, and also the amount of risk because of the validation, design, investigation that they need to do, all the expensive tooling is eliminated. So there's a huge cost benefit as well. And next, we also have an story from the healthcare sector. So this is actually uh, played a life-changing role in surgical planning. So this case involves a patient with tumor in his bone, and the challenge was to plan the surgery with absolute precision. So in complex surgeries like this tumor removal, precision is everything in surgeries. So they need to identify in the exact manner that they need to cut and replace this tumor. So traditionally, the planning used to rely just on 2D scans, surgeons' experience, which can lead to a lot of uncertainty, and there's a lot of risk, and it takes longer time for the surgery, higher chance of error. Also, it is difficult to achieve perfect alignment for the reconstruction. So here's where the technology stepped in. The team started by printing, by 3D scanning the patient's anatomy, capturing every detail of the bone and the surrounding structure. Using this data, they had designed the custom cutting guides and drill guides tailored to the patient's specific geometry, bone geometry. So these guides were then 3D printed using polymer, allowing the surgeons to actually physically hold and test them even before the operation, right? So the approach has actually given the team a clear roadmap and visibility on where to cut, how to remove, how to position, how to replace, how to transform the planning from simple guessworks to into precision rehearsed process, right? So the surgery was much faster, much safer, much accurate, and tumor was removed successfully. And after reconstruction, there was a perfect alignment, and that is where this technique has. That is where how the industries have started to adopt. And if you look at another sectors segment similarly, uh, which uh, which has been which is being done widely again, is the pelvic bone, replacement and pelvic bone reconstruction of the pelvic bone. So this also is similar, like where they had to rely on 2D imaging and surgeon's experience. Now with the 3D printing in hand, they're able to exactly visualize where exactly is the issue, how they can optimize the design for implants. In fact, that now there are metal implants, polymer implants available uh, that go hand in hand with 3D printing, and all these are printable, and they're also biocompatible in nature, and very good use case of this technology altogether. And then we also have a case about the aerospace industry, where there's a industry that mainly works on drones. And if you look at aerospace or the drone manufacturing sector, every gram matters. So the challenge was here to produce a structurally uh, good component which is lightweight, yet it is strong enough to handle the high loads and vibration during the flight, right? So traditional machining or through aluminum was an option, but again it adds weight, and it requires again tooling. And if you want to consider injection molding, then again the lead time, the cost for low or low volume production is very high there. So when the team needed a solution that combined strength, lightweight properties, also the design flexibility, this is where they turned towards polymer 3D printing with carbon fiber reinforced composites. You also have glass fiber and other things. In fact, in my previous organizations as well, we were using glass fiber composites, but all those were conventionally made. It used to take tremendous amount of effort to actually build these frames. Now with 3D printing, the design can include some internal lattice structures for reproduction. You can optimize the geometry for the aerodynamics, and which are actually not possible in conventional techniques. And in the end, a functional end use part can be actually printed and used. Nearly, I think about 40% reduction in weight compared to aluminum, and it also improved the flight time. Also under stress, it was still maintaining and withholding, and the overall time that used to take beyond 4 weeks now was happening in less than 10 days. And in fact, for all the uh, small batch volume productions, significant amount of cost reduction has been observed. And next, coming to another success story, this is with regards to one of our customers. In fact, uh, they work in the e-mobility sector, specifically in electric vehicle related components. So they use 3D printing for fitment check, visualization, and also they are actually using in end use applications like materials like ABS. They are using it for cooling system parts, production covers. So in fact, they have printed large parts as big as that goes for about 60 hours without interruption, and then being used in their end use applications. And again, a very good case that actually uses polymer 3D printing in end use. So with this, uh, I would like to next take upon some of the innovation enablers. So if you look at polymer 3D printing, you know, I mean, be it reducing lead time or being able to do complex design. But beyond all this, what is actually driving this transformation and where it is actually headed? That is where we're going to next. So in this section, I'll talk about a little bit of on the innovation enablers and what is a future landscape, and we'll explore some of the key factors that are actually pushing polymer 3D printing forward. And it's a core product. It's a core part of some of the production strategies. So let's dive into some of these. So if you look at the enablers, we can categorize them into this four segments. The first would be the model. Model is an enabler, and how the design is developed, and you cannot always go with CAD models that are created for machining and molding, which don't really translate for well for additive manufacturing. And that is where design for additive manufacturing comes into picture. Then we also have the software that impacts it. In software, if you look, the build preparation softwares play a major role uh, in enabling this technology. They um, and next comes the material. Again, material is also very critical. Uh, the quality of material, the source of these materials, how well it's blended, and the kind of compositions that come out of it eventually affect the overall quality of the printed parts. And last, the machine itself. Like, even if you have the best design, the best software, and the best material, the machine is the one that is going to enable the printing. And having a robust system to be handling all of these is what is very critical. So I'll take you through each one of this in detail. So first, if you look at design for manufacturing, so like I said, if you go with conventional design rules that you use for machining or molding, it will limit your capability and creativity. So that is where DFAM will flip that approach. It will encourage you to, go with unique designs, go with complex geometries. In fact, some of the issues that come, or come when you don't consider DFAM is like, say for example, if you have sharp edges, or if you're having some overhanging features and features that are too thin to be printable in nature. So those can affect your end use part. So that is where DFAM isn't just a design method, it's a mindset shift. You need to shift your mindset towards building functional part which can make use of AM, uh, the complete full potential of AM. So that then you will get much lighter, stronger, and more efficient part if you compare it with conventional techniques. So, and then the next thing is, if you look at the model, even the model's tessellation quality plays a major role. In fact, usually the process starts from model to STL, to a STL file, or the mesh file. And when you're doing this conversion, even if your STL resolution is very low, that also can impact your part outcome. So that is also a little critical. Again, there's a balance between high tessellation versus your the quality that is required, because even if you overload, if you end up overloading the tessellation, then it will eventually overload your softwares as well, which you need to find the right balance between the resolution and the quality that you desire. And also, once you adopt methodologies where you are doing reverse engineering, or if you are doing 3D scanning, there can be certain elements. If even, in fact, if you see in one of the previous uh, medical models that I showed you, where it comes from uh, it comes from a scan. So there could be some missing elements, there could be some errors in the scan. And when you look at STL errors, the two common is non-manifold edges, the intersecting faces. So non-manifold edges basically where you have a edge which is shared by more than two faces, and when there is a hole in the mesh. So basically, you can think like a leak in a water tank. So if the surface is not watertight, then your slicing software or the software will not be able to figure out what's inside and what's outside. And then you will have a disconnect between the surface, overlapping shells, and intersecting faces. And again, uh, if you don't get the STL right, if the mesh right, then it may lead to uh, errors in the end part. So, and then if you look at the next, that is the software. So if you look at software, when we talk about software, in fact, the software is actually the brain behind the printer. It actually converts your 3D model into instructions that the machine can understand, right? So the entire magic lies in the printer parameters. Setting that will actually directly affect your quality, your strength, as well as the speed. So if you look at, for example, layer height between 100 microns to 300 microns would vary. That will impact your surface quality. So finding the right balance between your application and the speed at which you need them is going to be a game changer. And then the infill density. So if you look at the infill density, again, not all parts really require solid fills. So certain parts you can, maybe do 20% hollow, 30% hollow. You can also add different structures. Maybe it could be honeycomb, triangular, lattice, rectangular parts. So it's, if you go with prototyping, then lower infill density makes more sense. And then if you go with much more functional and stronger parts that you require, then again you can identify the right pattern density, uh, and go with the strength and efficiency there. And then again, your orientation, finally, how you position the part also is going to play a major role. And the surface finish, if you look at circular features, the best orientation is actually vertical. But if you go with the horizontal orientation, then you have a limitation where the circles are not circles anymore. It becomes a little bit oval or like a teardrop. So in short, software and its parameters like layer height, infill density, or the orientation, and various other parameters within the software, they are the key to balance between speed, strength, and quality. And coming to uh, the next enabler is the material. So if you, when we talk about material extrusion, the choice of material is also going to be a game changer, because that will determine your strength, your flexibility, or if you need any heat resistant component, or if you need any functional part, if you need impact resistant part. So if you look at the earlier days, the thermoplastics like PLA and ABS were the most demanding and being used. But now the industries are moved towards composites, polymers, high performance polymers. So it's definitely going to impact your overall uh, performance of your part. So choosing the right material is the key. And if you don't opt for the right material, and if you compromise on it, then you may end up with uneven surfaces, uneven textures, stringing kind of effects. If you look at the image, like, when the quality is not good, or if there's a lot of moisture absorption, for example, in materials like nylon, PETG, they are very hydroscopic in nature. They absorb moisture from air. Even if you leave it for a few minutes, they capture moisture very easily. So storing the filament in the right manner, and drying them, making use of it in the right manner is very important to get usable parts and stronger parts. And then you will also come across impurities in the material. Again, you will not really know by looking at the material, but there can be impurities in the materials, whatever fillers are being added, which are mixed during the manufacturing stage. And that can eventually affect during your print. Like, it could clog the nozzle, it could disrupt any extrusion events, it could grind the material, blobs can come, layer deformation can happen. So all this uh, will is a key for your material. So always choose high quality filaments, also from trusted suppliers, and don't really bargain on the brand that compromises purity. So because that is what is going to affect your uh, functional parts, right? And then you also have inconsistency in the, maybe in the diameter of the material, or the kind of material that being used. So that also can lead to, weak walls when you're printing thin features. So those kinds of elements will definitely affect your overall part. So always go with filament with has strict quality adherence, tight manufacturing tolerance, consistent compositions, and also go with premium grade materials, so that you will have predictable melting and, smooth flow of the material in the material extrusion technology specifically. That will really change the way you use 3D printing for your application. Next, coming to the final contributor, that is the machine itself. So machine is the one that will actually print these parts, right? So machine is the critical component here. So if you look at, you know issues like warpage, cracks, all these are bound to happen in polymers. And it's not just in 3D printing, even in conventional manufacturing, you will come across warpage, cracks, mainly because the way the material is being handled by the machine. So even if you get the best material, best software, like I said, the machine is the one which is ultimately going to print these parts. So there like features like heated platform, heated chamber, that will regulate the uh, way the material behaves within the machine, the way the parts are being printed, and eventually it ends up affecting your overall part quality. And one of the major challenges that you will actually face in material extrusion is the layer addition. Poor addition, like 50% of your part is, or the job is done if your addition is right. So getting that right is what is very important. And to enable that, you need to have systems that are intelligent, that are smart, that are capable to handle the platform leveling, large, when you're going with large parts, large platforms, edge to edge. If you want to print edge to edge, then platform leveling is the key. And having features like mesh level, um, kinematic levels. So those are the ones that will actually eliminate your challenges that you face with addition. And then coming to issues like you may face certain issues like vibration, ringing, like you've seen the images like ghosting effects. So these are directly impacted from the machine itself. So how good your gantry system is, how well they are built, if they're using precision rails, or if the belt mechanisms are belt driven, or the gantry mechanism, what kind of actuator you use, what kind of motors that you use, all those machine related components, the gantry related components are going to be very critical in terms of the machine, because uh, there should be no compromise, because this is a moving part. So in the moving part, there should be no compromise, and that is where your gantry system is going to come and help you in delivering consistent result back to back. So that repeatability will be possible only if you have a robust mechanism. And then again, like even if your material is good, uh, you still may sometimes face moisture related issues, because the material itself is like that. Because if you consider PLA and PETG and some of the nylon materials, they are by nature hydroscopic, so they will absorb moisture very quickly. So that is where, like having the ability to dehumidify them or store them in a manner that it will not absorb moisture will really help in getting the best results. And then again, stringing also is material related sometimes, and sometimes your machine also should be able to handle that. So that is where certain self-cleaning mechanism can really come into picture and help you eliminate these kinds of issues. So on the whole, these four uh, enablers are extremely important in extrusion, material extrusion, specifically in FDM and FFF technology. And that is where you these are the key enablers, like that will help you enhance the overall quality. Now, next, coming to the trends, like if you look at the kind of innovation, material extrusion has already come a long way, because initially it used to be a simple desktop printers. Now it is being rapidly evolving into different materials, smarter process, much more advanced technology. If you look, the future is being driven by advanced composites, conductive materials, like I told, and also certain AI related integrations, process automation, uh, high speed high speed printing. All these is what is going to drive the future in this technology. So if you look at advanced composites, if you look at composites, these carbon fiber composites, glass fiber, nowadays I even see Kevlar based composites, because they combine the lightweight nature of polymers with the strength of fibers. So eventually making the part as strong as the metal, but much lighter. So aerospace, they use a lot of carbon fiber composites. And for drones, like I showed you, then some structural component, uh, some performance parts. All these are uh, uh, definitely require advanced composites. And then we also see conductive materials. So you can imagine printing not just mechanical part but also composites with electrical functionality, right? Conductive filaments will actually allow you to embed circuits, sensors, even antennas directly into the 3D printed part in a single process, in a single machine. So that opens doors for smart devices, IoT applications, lightweighting of electronics, where the structure and the circuitry can be integrated in one print itself. So it's a game changer for industries like consumer electronics and medical devices. And if you see the trend of AI and making use of AI, the process automation AI integration is going to be a key. All modern printers are becoming smarter with real monitoring, predictive maintenance, then AI driven parameter optimization. AI can actually analyze your print data, they can predict your failures, they can adjust the parameters dynamically for better quality. So combining automation features like automatic calibration, filament detection, cloud-based control, material it makes material extrusion scalable for industrial production. So this is the way or the direction in which I see polymer 3D printing going into the future. And you can see a lot of advancements coming through in the near future. So with this, I would like to conclude by saying just one statement that polymer 3D printing isn't just shaping parts, it's shaping the future of manufacturing. Thank you so much.